So, yes, I represent today the team of very persistent people who promised to the industry about 30 years ago that quantum dot lasers will be everywhere. And, luckily, it looks like in some way it's coming. But today I want even to talk more about like free space, optic communication, both, for terrestrial and even space. So, here you see this picture, right? So, from my understanding, and I will be really looking for commands from the industry. Why people stick to 1.5 micron for free space communication? Because of what? Availability of components, power level, which can be achieved in EDFA. Because in terms of, hydroxyl ion absorption, water absorption, and in terms of eye safety, 1.3 micron is better in both. And actually, I was surprised myself when I learned it, because I expected the longer the wavelengths, the better the eye safety. But nevertheless, and recently, even though our main focus is similar to the previous presenter, but recently we see really growing interest to O-band for terrestrial communication and other applications. So, and here probably we can help. So, and because what we can achieve today with our quantum dot lasers, and remember, these are indium arsenide islands embedded to gallium arsenide. So that's why the band gap discontinuity is really huge. And that's why we have very good temperature performance. So we basically can keep the same performance up to 105 degrees C. So we're kind of matching temperature of operational temperature of photonics to highest operational temperature of electronics. So we are working in order to boost power conversion efficiency of DFB lasers 1.3 micron up to 30%, and I hope to present it at OFC. There are many components. Somehow nature, I would say, help us, because we have much lower noise in our semiconductor optical amplifiers, and we're getting very high power in semiconductor optical amplifiers at 1.3 micron. So today we already can get power level at in O-band from quantum dot SOA without tapered design. It's a very narrow stripe, like 3-4 micron, single mode, single frequency without tapered design, up to 1 watt CW at 85 degrees C encode. And we're working toward a higher power level. And yes, we like 2006, we discovered, I would say, comp laser, but not type of in light represented, but kind of mode log based on quantum dots. And here we also work for these AI ML clusters with WGM arrays and so on. So my point is, it looks like, 1.3 micron is the best wavelengths for both to travel through fiber, to travel through air. And because we believe we can go to power level of up to several watt from semiconductor, we can support people developing also satellite free space systems in order to make smaller size, and more efficient transceivers as well. And economics of gallium arsenide in a volume will be much better than indium phosphide, because we can go up to 8-inch wafers. And today, world consumes like 3 million of 6-inch gallium arsenide fully processed wafers for LED, for VCSEL, face recognition, and for RF. And also in O-band, again, I'm trying to pitch 1.3 micron, because very often we hear, in 1.5 micron, we have the whole component base. But the volume which will be driven, which will be produced in 1.3 micron for O-band, for cloud and AML clusters, it's like 50 million links in several years from now. So we prove reliability, our lasers kind of don't die. And the funny thing that, because this is islands, and we're 1,000 times more radiative, harder, rad is 1,000 times better compared to quantum well devices. So my question so no doubt for me, no question for me for datacom, but now my question whether 1.3 micron platform can be utilized in terrestrial free space optics, and maybe even in satellite, and also from orbit to the ground. And here we will be looking for partnership and joint developments.